All right, let's have a look at this one. It says a glass U tube with a uniform diameter of 0.85 centimeters is used to determine the density of an oil. As shown in the figure above, a 24.5 centimeter column of water, so right here, balances a 27.2 column of the oil. So that's the column right there. So that the interfaces of A and B of the mercury with the other liquids are at the same height. The density of the water is about 1,000 kilograms per cubic meter. So even that description can make this a little confusing. It's like we have this U-shaped tube, it's filled with mercury, and then on top of that we pour some water, and then on top of that we poured oil until the two sides of mercury came into balance here. So the very first thing is they say calculate the density of the oil. Well, we know because the mercury here at A and B is at the same height. You know, if the pressure was greater over here, A would be pushed down beneath B there. But A and B are at the same height, so they must have the same pressure exerted on each of them. So the way we can write this sort of is that the pressure being caused by the oil has got to be equal to the pressure being caused by the water. Now, pressure caused by being submersed beneath a fluid carries the equation density times gravity times height. I'll put a little O there for density of the oil times the height of the oil. So that's one side, and that's got to be equal to the other side, which is density of the water times gravity times height of the water there. Gravity's on each side, so that doesn't matter. You could do this experiment on the moon and it would work out exactly the same way. So if we want the density of the oil, let's rearrange. Density of the oil will equal density of water times the height of the water divided by the height of the oil there. So now we're just ready to plug in and solve. So density of the oil is, density of water is 1,000 kilograms per cubic meter. If the heights are both in centimeters, that will cancel out. You don't have to convert it. So I'm just going to go ahead and write 24.5 is the height of the water, and 27.2 is the height of the oil. So you can see here, because we're dividing by a bigger number, it's obviously going to get less than 1,000. And so if you work that out, you get about 901 kilograms per cubic meter. Again, it makes sense that the oil is less dense than water because the height of the oil is greater. So to get to an equal pressure, it must be less dense. All right. Next one here, it says calculate the absolute pressure at B, the interface between the water and the mercury. So absolute, that's important. So we're trying to find it right here at the interface between those two. So again, the equation for pressure due to a fluid is density times gravity times height. If you want to make this the absolute pressure, we've got to add in atmospheric pressure there. So let's start to plug in. It's as simple as that. So the absolute pressure is equal to the density of water is 1,000 kilograms per cubic meter. The gravity is 10 meters per second squared. The height, now here we do have to convert it into meters. So it's 24.5 centimeters. So you've got to change that to 0.245 meters. And then we have to add in atmospheric pressure, which they allow us to round off to 100,000 pascals. So working this out, multiply these three out, add in your 100,000 here, and you should get that the absolute pressure is equal to about 102,450 pascals. All right, next part is they say we have a new tube here. A new tube identical to the U-tube except for a cone shape on the left as shown above is filled with the same volume of mercury that was in the U-tube. The mercury is at the same height on both sides of the new tube as it was in the U-tube as shown by the dashed line. So A and B, same as before. The same volumes of oil and water that were used in the U-tube are now poured into the new tube on the left and right respectively. So this water over here is poured in until it would fill up 24.5 centimeters just like before. So it says indicate the new position of B relative to A. So B is over here, and A is over here. So we'll fill it with this oil, the same volume of oil as before. So to answer this question, what will happen to B and A? It's basically saying, like, think of it as like a seesaw here. So is the pressure still the same? If the pressure is still the same, then the seesaw will remain balanced. If it doesn't, then one side will tip. Well, if you think about it, remember, because pressure is density times gravity times height, this shape here allows the height to be less. So it does say justify your answer. So less height for the oil means less pressure. So A will not be exerting as much pressure as before. B will be greater. So this side will actually dip down. The mercury will start to rise up into here, and here it will start to drop. So B is now below A. The last part here says a small piece of wood with density less than that of oil is placed so that it floats in the left side of the tube. Indicate whether the pressure at the bottom of the tube increases, decreases, or remains the same. Well, there's a couple ways we can think about it. One is we can just understand that if we put a piece of wood right there, we get that it's going to exert a force and therefore more force, more pressure on this side. Another way you can think about it is you get that if you dip this in here, you're going to displace some of that fluid. Like you put something in a bathtub, the water goes up. So if you put that cube in there, it's actually going to cause the volume to go up a little bit before it floats there. So, and that will make the height greater, and that would make the pressure greater. So either way you choose to think about it, the pressure at the bottom will increase.